Okay, I will be presenting this paper, representation learning by learning to count. I'll start with some background. I will define self-supervised learning in contrast to supervised learning. In supervised learning, we have a set of images and we have labels for them, and we extract some features from the images and we try to classify them. And given those images and labels, we learn some representations or features. Now, once these features are learned, they can be very useful in transfer learning fashion. We can use them for object classification, object detection, and semantic segmentation. This supervised learning has its problems because it requires human annotation. The process of collecting human annotations is costly, error-prone, and time-consuming, so we want to avoid that. So the alternate is self-supervised learning. In self-supervised learning, instead of trying to classify images, given a set of images, we define a pseudo task and we try to solve that task. And during the process, we still learn some useful representations. Now, this process has its advantages that it doesn't require human annotation, so it's cheap and scalable. So we want to learn good representations. So the property of good representations is that they will tend to cluster similar images together in the representation space, and they will push away dissimilar images like they are in this figure. So how do we learn good representations? For example, in deep learning, what we do is we have a set of images and we have labels. We show the network an image and we give the network its label. Then we give the network a similar image, so image from a similar class and the same label, and the network tends to learn the similarity. Then we give a dissimilar image and a label for that, and this way network learns the similarity and dissimilarity. Now the idea of this paper is that this similarity can be based on counting. So the idea is that suppose that we have an image and somehow we can count the number of features in that image. Now it shouldn't really matter if I count the number of features in the image, or I divide the image into patches and count the features in those patches and sum them up. So the feature count should be equal in both the cases. So they implemented this idea on a modified AlexNet, and they defined two image operators. So what they did is, given an image X, they downsampled then that image and they applied a tiling operator. So the tiling operator divides the image into 4 equal tiles. Now they have 5 different images, and the sum of the tiles, some of the features in tiles should be equal to the features in the original image. Sorry, in the downsampled image. So this constraint should be satisfied. That
so the downsampling is not applied, for the tiling. Tiling, you just take the 4 pieces.
Yeah, exactly.
But downsampling applied to the original image.
Yeah, exactly.
Because you say other way.
Yeah, sorry. I probably. Yeah. So the downsampling is applied just to make sure that the input to the network is fixed. So this constraint gives us this simple loss function, and they try to optimize this loss function. So there is a problem with this loss function, that it's very easy for the network to learn to output 0 for every input. And this problem is called least effort bias. And to avoid this problem, we can use a contrastive loss. And the idea of contrastive loss is that it will force the network to learn the features or representations which are useful for discrimination between different classes. So here's the idea of contrastive loss. So in the original loss functions, we had these 5 patches. But for the contrastive loss, other than these, we also randomly pick an image Y from the dataset. Now, since this image is picked at random, it should be different from it should belong to a different class than the image X. Now, we want to so they added this extra term to this loss function, which makes sure that the network will now learn the features which are now useful for discrimination, because this term will be higher when the network fails to discriminate between these two objects.
So a simple way to say that the count in those whole image downsample and the summation of the 4 sub-images should be different from the count in the image Y, because it's very different.
Yeah, exactly.
That's what they want.
Yeah, exactly. That's right.
So the second term, the summation term, can also be. I mean, instead of that, we can also use the first term that is used in the first part, right? For example.
Yeah, the downsampled image. We can use the downsampled image in its place, but they haven't discussed it in the paper, so I'm not sure. Yeah, but
so
you can.
So the second term, in the contrastive loss term, there is a summation that we are using.
Yeah.
Instead of that, we could. I mean, intuitively, you would think that they should compare the features from the image Y to the features from image X directly instead of the parts. So instead of that,
here should be, you say here should be Y?
No, X.
It's X, DJ X.
So instead of this term here, we can have this D of X.
No, but I mean, there's a summation thing what matters, right?
Summation.
It probably makes a difference, but they haven't discussed it in the paper.
Yeah,
so,
you can add that point. You have some idea about it? No. I think because it's symmetric, is that right? So you're saying downsample X, and it should be same as the tiles of X, right? Yet downsample Y, it should not be the same as the tiles of X. So it's kind of makes sense.
Yeah, it makes sense.
It's more symmetric. So you want to do the other way. I don't know.
I mean, downsample of Y should be different from downsample of X, right? So we could also take that difference there.
Another loss, you mean?
No. Instead of the summation.
I think you need a summation, because the whole idea is summation is important here, right? The first term you have summation. Yeah.
I think for the Sandwich network, right? The counting part is, I mean, that's where they are trying to use that counting part.
But the counting part is there in the first term of the loss already, right? So there we are trying to make sure they are equal.
Okay, so let's continue, then we can discuss that.
Okay, so we are done with the method. So now I will discuss experiments and observations. So one of the first observation is that the activations of the neurons are very sparse. So we know that AlexNet has 1,000 neurons in the last layer, and if you see this graph, we can see that the average magnitude. There are very less neurons which are actually firing. So they stated in the paper that only 30 neurons have non-zero magnitude.
So each neuron will give you like a scalar value?
Yeah, it will give a scalar value.
So what does magnitude mean? Just absolute value?
So I think they have averaged the activations over whole data set, and then they have normalized it because you can see the peak is at 1.
On the positive.
Yeah.
Maybe negative.
They don't have negative values because they applied a ReLU at the last layer.
Yeah, okay.
So they don't have.
just and they have I don't know why they are saying magnitude. It doesn't matter if they all are positive, right?
Yeah.
And this is scalar.
Yeah, these are scalar values. So as I discussed earlier, learned representations can be used for transfer learning, and there are three tasks, famous tasks defined for transfer learning. We can give an image, we can classify it. For classification, we have to provide a label. And there is a detection task. For detection, we we have to provide the bounding box around the object as well as the label. And for segmentation, we have to label each pixel in the image. So they evaluated their learned representations on partial dataset, and here are the results for that. They have best results for classification and comparable results for detection and segmentation. So they also tested their transfer learning potential on ImageNet, and here what they did is they extracted features from different convolutional layers. AlexNet has 5 convolutional layers, and they in each of these experiments, for example, for first column of experiment, what they did is they extracted the features from first convolutional layer and trained a fully connected layer on top of that, and tested on ImageNet test set.
So when you say convolution layer 1, what does it mean? Because they have lots of feature maps, so they convert them into feature vector or something. Because I thought normally you do the one layer before the fully connected, right?
Yeah,
The
exactly.
features from there.
What they said that they extracted the features from convolution layer, and then they resized it to get, I think, 90K or 9K features, and on top of those 9K features they add a fully connected layer. So they did resampling.
And these all other methods are doing that.
Yeah.
But that's
So
a
for
weird way, right? Because I haven't seen that people just use the feature maps after convolution layer 1
yeah,
and to do recognition, because normally I've seen FC7, FC6, those are fully connected.
yeah, but
These are the different.
yeah, but this experiment is designed to test that their convolutional layers are learning useful representations. So, for example, in second layer, what they did is they freezed the first layer and second layer, and then they extracted the features from second layer, and again trained a fully connected layer, but they didn't update the weights of first or second convolutional layer. So this way, they made sure that the representations that they learned in a self-supervised way or unsupervised way are there. They didn't.
Okay, so
Yeah.
then maybe that will clarify. So these are not the features from convolution 1, but these are when they freeze convolution 1 or something? Or
Right.
where the features are from the FC6 or FC7, right? Where the, because it may be just a way they explain what the staple is. See, they can say that they are, you are saying when they do convolution 2, then they do what? They freeze what's there?
They freeze convolution 1, convolution 2,
Yeah.
and they defined a single fully connected layer on top of convolution 2.
Only 2 layers.
Yeah.
Okay. Okay.
Only
So
3
you
layers.
define that and you do that.
And then they test.
And then the features are getting obtained from the one layer before
One
that,
layer, yeah.
not a convolutional layer.
Yeah, exactly.
Okay. So that clarifies.
Yeah.
Okay.
Uh, okay, they had okay. So they had the similar setting for another experiment, and this time they tested on places dataset. Places dataset is similar to ImageNet. It's a classification dataset. It has more than 10 million images and 434 classes. So these are some of the images from places dataset. As you can see, this is very diverse and challenging dataset.
So these are not like simple objects, like
Yeah.
window, nature,
These are
different.
these are actually scenes from real world. and their network performed really well on places dataset. You can see that on most of the cases, it has beaten the state of the art. Then there are some ablation studies. So there are several factors which can be modified in their training. So they used a downsampling method, downsampling operator, and there are several options available for downsampling. And so, for example, and they can vary the training data size. They can either use RGB images or color images, and they can change counting dimension, the length of the final layer. So they did some tests on all these factors. So the first row here, they reduced the counting dimension to 20, and they noticed that performance downgrades a little. So this last row shows the best performance. This they achieved by mixing all the parameters, all the factors that they can change. So
I mean, this system you go back, it mixes the RGB and color.
yeah, they mix RGB and color. Yeah.
The training shows 1.3 million.
Yeah.
And counting dimension is
1,000.
So that gives you the
best result. Yeah. So they changed the training dataset size, and they noticed that indeed the performance degrades when they have less data for training. They tested with the RGB images and grayscale images separately, and they noticed that for RGB images their performance drops. And they tested with 4 different interpolation methods, and which has similar sort of results. So, in self-supervised, when we are training in self-supervised way, we don't really know what the network will learn. So to see that the network doesn't is indeed learning useful representations, and is not learning some other it's not learning on some other cues which are not really useful for us. They did an experiment where they tested whether their network is learning their downsampling method. And so what they did is, at training time, they downsampled with one of the available downsampling method, and at test time, they tested with all of them. And indeed, they noticed that their network is learning their downsampling method, which is not good. So in the previous table, you can see that when they mix this downsampling method, it attains a better performance.
So they're confusing the.
Yeah, they are confusing the network. So this experiment is designed to show that indeed the network is learning to count useful features. So one of the problems is that the network can learn to count low-level features like edges, number of edges, and number of corners, stuff like that, which are not really useful. So they design an experiment where they take an image window, and they iteratively grow the window so that more content is visible in the window. So if you look at these images from left to right, more content is visible in the image. So the network should give a higher count for the image at the right, and the low count for these images. And they so they changed this the scale of the window from 0.5 to 0.95 at 0.05 interval, and indeed they noticed that when they changed the scale, increased the scale, count indeed increased.
So it increases well for the high norm, but not really for the low norm.
Yeah,
not that much.
Exactly.
And high norm again is what?
So high norm is a set of images which already has a very high count. So they collected 2 sets of images. For one set of images, they only collected images with high count, and for other they collected images with low count. In this experiment, they tried to show that once again that the network is counting useful features. What they did is for ImageNet, they extracted the 16 images which with the highest count. So these are the most activating images from ImageNet, and these are the least activating images. And you can see that least activating images are patterns and texture which are not really useful to count.
Which means the count vector for the left image is
Was high,
large,
yeah,
high as compared to the
as
right.
compared to the right ones.
And even though on the right one, actually, if you start counting bricks and so on, those things.
Yeah, exactly.
But they're talking about higher level features like bags and
Yeah, exactly.
bicycles.
They did the similar experiment with similar setting on Coco dataset, and these are the results for that. So another experiment which can demonstrate that the representations learned are indeed good is image retrieval. So what they did is, given a query image, they retrieved the nearest neighbor image from ImageNet dataset, and you can see that matches are indeed similar to the query image. They did a similar experiment for Coco dataset. So the last experiment, they tried to look at the individual neurons, and they tried to look at the images which activate the neurons the most. So this is the set of images, eight images which activate a neuron 1, and this is for neuron 2, neuron 3, and neuron 4.
Which means the neuron one has the highest activation or something?
Yeah, it means that neuron 1 has highest activation on these images. So they are showing that each one of their neuron is learning to fire on different type of image. And similar experiment for Coco dataset as well. Yeah, that's it.
Okay, good.